Hey guys, welcome back to the channel. So in this video, we would be solving this today's daily LeetCode challenge, which is count submatrices with all ones. So we are given an n into m binary matrix, which is mat, and we have to return the number of submatrices that are having all ones. Okay, so let's consider this first example. So here the answer is 13. So let's count the submatrices with all ones. So here it is mentioned that there are 6 rectangles with side 1, which are 1, 2, 3, 4, 5 and 6. Then there are 2 rectangles of side 1 into 2, which is this and this. And then we have 3 rectangles of side 2 into 1. Okay, so they are this and this part. Okay, and then we have 1 rectangle of side 2 into 2, which is this square. And then we have the last rectangle of size 3 into 1, which is this column. Okay, so let's see how we can solve this problem. Okay, so we took the same example and here we have our answer as 13. So now for every cell we have a couple of options. Like this cell can be the starting point of a particular rectangle. Like let's say we have some rectangle, a particular rectangle is like this, and then we have this starting cell here, so that from this cell we can extend to this right part, or we can extend this down part, and then we can extend to this diagonal part to get all the squares, or I would say all the rectangles that can start from this point. But here we can see that if we calculate the answer for this part, then it is of no use for other parts, because for this again we have to calculate the answer. Like this would be for the down part, the right part and the diagonal part. So calculating this will not be efficient. So for the calculation of a rectangle, we have to choose another cell. Let's say I choose this cell. Then if I choose this cell, then I can reuse the values which are calculated here. Similarly, I can reuse the values which are calculated over here. Also, I can reuse the values which are calculated in this diagonal part. So this would be an optimal choice for me. So what I can do is, starting from every cell, I can see how many cells are there, like how many rectangles are there which is having this cell as the bottom right corner. So let's start from here. Here I will see that on the left there is no cell, and on the top there is no cell, and on the diagonal it is empty too. So let's create some matrix here to store all the answer values. So now for each cell, what we will do is we will maintain the count of how much can be extended towards the top, towards the left and towards the diagonal part. So we will consider this matrix and we will store the values as left, that is the number of cells it can be extended towards the left. Then we have the number of cells that we can extend towards the top. Then we have the diagonal part, that is the number of cells which we can extend towards the diagonal part. And then for this we have 0 values towards the left, 0 towards the top and 0 towards the diagonal. So it would be 1, 1 and 1, since this is the only value which can be extended towards any part, and this is a particular rectangle with side 1 into 1. So we have 1, and then since it is 0 for this part, we'll just write it as 0, 0 and 0. Then for this part, towards the top we cannot extend it, towards the left we cannot extend, and on the diagonal also there is no values. So it would be 1, 1 and 1, because this was 1. Okay, so for this cell now we can see that towards the left we have 0 values, so it cannot be extended towards the left, and since this is 1, we write it as 1 only. Now for this, on the top we have one cell which is having 1. Okay, so we can extend it further, that is this one plus 1 for this current cell, now it gets 2. Okay, and again for this diagonal part, in the diagonal we have 0 elements. Okay, so it is still 1 because this was 1. Okay, great. Now coming to this cell, on the left part we can see that there was some value 1. So in the left we were having 1, and since this cell is itself 1, so here it will be 2, because we can extend towards the left having 2 values, this and this. Now for the top part we have 0 towards the top. So as this was 1, we will just write 1. And for the diagonal part, here we can see that it was 0. So we cannot extend it towards the diagonal part, because if we extend it something like this, then still this is 0. So doesn't matter if there are ones in this and this value. So basically we took the minimum of this, this and this, and we'll just consider it. So the minimum here is 0. So it was 0 plus 1, since this is the cell having 1. So we have 1 here. Okay. So now for this part we have 0. So we will just simply write 0, 0 and 0. Great. Now for this cell on the left we have 0 values. So it is 1 because this is a cell containing 1. Then on the top we can see that we have 2 values, that is the 2 cells having 1 in the upward direction. So we will add plus 1 to it, because again this is a cell having 1. So it gets 3. And here towards the diagonal we don't have any element. So the minimum of this, this and this. And again this is a cell containing 1. So we get here as 1. Okay. So now this is interesting. For this cell on the left, we can see that we have 1 value. Okay. So 1, and since this is 1 element, it is 2. And for top we have again, here it was 1, 1, and then 1 plus this current element, which is 2. And now for the diagonal part, since these all are ones, these all are ones, so the minimum here is simply 1 and 1 for this current cell. Okay, so we have this 2, which means that we can create a rectangle having sides 2 into 2. Now for this end we again have 0. So we'll just write 0, 0 and 0. Okay. So for each cell, now we know that how many rectangles can be formed such that this particular or each of this cell in this matrix is the bottom right cell. So now the answer is the summation of all these values in the particular cell, and we do this for all the cells, minus what we do is minus of 2 into the number of cells having 1, that is the number of cells, number of 1 cells I would say. Why? Because for each of this one we calculated 3 times in the left part, the top part and diagonal part, and since we wanted only ones for a particular cell, so we will reduce it 2 times for each cell. So the answer would be, for this we have 1, 2 and 3, which is 3, plus here it is 0, and then again we have 3, plus what we have is 1, 2 and 1, which is 4, plus we have 2, 1, 1, which is 4, then we have 0, then we have again 5, plus we have 6, plus 0. Okay, so the answer would be 3 plus 3, which is 6, then we have 4, which is 10 and 14, then we have 19 and 25. Okay, so the summation is 25, and since at the end what we do is we do minus 2 into number of cells having 1, which is this first, second, third, fourth, fifth and sixth. So 2 into 6, which is 12. So the answer would be 25 minus 12, which is 13. So yeah, this is the answer. For this you can maintain this DP matrix and calculate these values. So here let's see what is the time complexity. So the time complexity is simply n into m, that is for this outer ith loop and jth loop for this matrix traversal. Then we have this space complexity as again n into m. Since we are keeping track of all the elements in this matrix, so we will need another matrix here. So let's see how we can optimize this solution further. So again, let's take this same example, and essentially earlier what we were trying to do is for every cell we were trying to see how much can we extend towards the left, how much can we extend towards the top, and then we were calculating the answer based on this. Okay, so now let's consider this cell. For example, for this cell, now we can extend to this towards the left. Okay, and we can extend towards the top till this point. Okay, and since here it was also 1, so the height for this part was same as the height of this part, hence we were able to calculate this in this same square. So we got 2 into 2 size square. So an observation that we can see is we can go towards the left till we have the cells which are having the same height as of the current cell, and then all these cells can be used to extend our current column. Okay, so here now we know that we go towards the left till our height is maintained. Okay, and then what we'll do is we will check how many such left cells are possible, and then we will calculate it based on our height, that is we will multiply it with our current height. So I would say the current height. So in this way we know that how much can be extended towards the left such that a full rectangle is formed. Okay, now let's consider this another example, 1 0 1, and again let's say here it is 1, so again it would be 1 1 1 1 0 0, and then we have let's say some 0 and 1. Okay, now here for this part we can go up to here, and here as it is 0, so we cannot go till here because at this point we came to know that the upper cell is 0 as the height was 1 here. Okay, but we require the height which is 2, so we got this as 2 into 2, that is the number of cells towards the left which are 2, that is this current cell and this cell, and then we have the height of this current column as 2, so the answer would be 4. So 4 rectangles can be formed which are this, this, and this, and this another one rectangle. Okay, so we got to know that we can form 4 rectangles for this part. Now we know that how many rectangles can be formed if these all values in this particular part are 1, and now we know that here it is 1, that is the height is 1 of this particular column, for this particular column. So what we can do is we can check, can we extend this further towards this our current cell. So we know that for this all elements which are here, the height is surely greater than this, which means that this can be extended towards our this current cell. So for every rectangle which can be formed with this as the bottom right corner can be extended towards this. So again we will add our this answer plus the number of rectangles which can be formed such that this is the bottom right corner. So let's say this is the left boundary, the answer at this left boundary. Okay, so in this manner we can calculate all the values for each particular cell, and then we can just simply add them in our final, let's say, answer variable which was initially set to 0. So now the challenge is how can we find this left boundary. So for this we can maintain something like a monotonic stack which will maintain the elements in the increasing order, so that we can get rid of all these elements from the top if they are having some height which is same or greater than our current height, and then if we have something which is having the height less than our current height, then we can keep that element. So let's try to see this in the code. So now let's understand this with an example. Let's say we have 0 1 1 0, then we have something like 1 1 1 1 1 1, and let's say here it is 1 and here it is 0. So first we calculate our matrix dimensions, then we maintain a height array to keep track of the height of each of this element in a particular row, and then we initialized our answer variable. We iterate over each of these rows, and while iterating we calculate the height of each of this row. So for this we have height 0 initially for all these rows. So now for each of the row we will calculate the height, that is we will increase it by 1 if our current cell is having element as 1. So here it is 0, so the height is 0. So now here it is 1, so we can increase our height, which was previously it was 0, so now it is 0 plus 1, which is now 1. And I'll just get rid of this 0. So again here it is 1, so we can increase this height, now it is 1. So here again we were having this 0, and since this is 0 we will keep it as it is. and then we maintain a stack such that for this stack we have the first element at the index which is having the height which is just smaller than our current height. Then we have the height which was actually present in that cell, and then we have the answer which we previously saw that how we can use this to calculate the values towards the right. So the answer is simply the number of rectangles which can be formed such that this particular element, or let's say this particular cell or any of the cell over here, is the bottom right corner of that particular rectangles. Okay, so what we do is for each of this element in the row we will iterate over them, and then what we will do is we will iterate over this stack using a while loop, and we will get rid of all the elements having height greater than or equal to our current element's height. Then once we got that element which is having height less than our current height, then we will maintain its index, and if the stack is empty then it is basically something like this part. If you consider only this particular matrix, then here all the elements are having the same height as this element, so we will maintain -1 because this is the part which is the boundary towards the left. Okay, this is the same thing. And then if this is not the case, let's say here it was 0, so if we start from here then the height was this which was same, and as this is the left boundary now, so we keep track of that index which was present over here. So in this case the index would be the index of this element, so we have this now, and then we calculate the answer of this part which is stored in our stack. So we got that previous answer, and now we calculate the current answer. So current answer was simply this part, this particular part, into the height of this. So what we do is we took the current height and into the number of cells which can be extended towards the left, which is this part, and then as we saw in the explanation we add this previous answer because this can always be extended towards this right, and then in this manner we got our answer for this current row, current cell I would say. So this we will just push it in our stack, so it would be the I which is the index, and then we have the height of this current row, and then we have the answer for this current cell which would be used for calculating all the values towards the right. So now we will just add this answer in our answer variable. So in this manner we will calculate this for all the cells, and then at the end we can just simply return our answer. So the time complexity here would be simply of n into m, because we are iterating over the rows, and for each row again we are iterating. And then we have the space complexity here, big O of m, because we would be keeping all the elements in our row in the stack, that is all the elements which is equal to the dimension of the column, and hence this is the optimized version of our previous BP solution. So yeah, this was a beautiful problem based on monotonic stack. Thanks for watching and subscribe to the channel for more such videos.